Have you ever wondered why a simple sheet of paper becomes as fragile as tissue when it gets wet? This seemingly mundane phenomenon reveals one of nature's most fascinating molecular secrets. While dry paper can support surprising amounts of weight and resist tearing with remarkable strength, the moment water touches its surface, it transforms into something almost laughably weak. The secret lies in paper's hidden architecture. Paper consists of millions of cellulose fibers derived from wood pulp, each measuring only 1 to 3 millimeters in length. These microscopic strands interweave like a complex textile, creating a network held together by hydrogen bonds between cellulose molecules. Under a microscope, dry paper resembles a dense forest of interconnected trees, each supporting its neighbors. Hydrogen bonding serves as paper's invisible glue. These molecular attractions occur when hydrogen atoms in one cellulose molecule are drawn to oxygen atoms in neighboring molecules. In dry conditions, millions of these bonds create a robust three-dimensional matrix that gives paper its structural integrity. Scientists have measured these individual bonds at approximately 12 to 30 kilojoules per mole of attraction force. When water infiltrates paper, it launches a molecular invasion. Water molecules possess their own hydrogen bonding capabilities, and they aggressively compete with cellulose molecules for bonding sites. Each water molecule can form up to 4 hydrogen bonds simultaneously, making them formidable competitors for the existing cellulose network. This competition fundamentally disrupts paper's structural foundation. Historical papermaking techniques reveal why this weakness exists. Ancient Chinese papermakers discovered around 105 AD that plant fibers could be suspended in water, then dried to create writing surfaces. However, they also noticed that their creations became vulnerable when re-exposed to moisture. Medieval European paper mills documented similar observations, noting that wet paper required completely different handling procedures. Water causes cellulose fibers to undergo dramatic physical changes. As water molecules penetrate the fiber structure, they cause individual cellulose strands to swell by up to 30% of their original diameter. This swelling creates internal stress within the paper matrix, stretching the hydrogen bonds beyond their optimal length and weakening their attractive force significantly. The lubricating effect of water compounds the problem further. Water molecules act as microscopic ball bearings between cellulose fibers, reducing friction and allowing fibers to slide past each other more easily. This lubrication effect, combined with the disrupted hydrogen bonding network, creates conditions where minimal force can separate the fiber structure completely. Scientific measurements quantify this dramatic strength loss. Research conducted by pulp and paper laboratories demonstrates that wet paper retains only 3 to 7% of its original tensile strength. The wet tensile strength of standard office paper drops from approximately 100 newtons per meter to just 5 newtons per meter when fully saturated with water. Modern technology has developed solutions to combat this inherent weakness. Synthetic papers made from plastic polymers, waterproof coatings applied to traditional paper, and chemically modified cellulose treatments can preserve paper strength when wet. These innovations find applications in marine charts, outdoor maps, and waterproof packaging materials where moisture resistance is essential. Understanding wet paper's fragility illuminates broader principles of molecular engineering and materials science. This simple phenomenon demonstrates how water's unique properties can dramatically alter material behavior at the molecular level. The next time you accidentally spill water on important documents, remember that you're witnessing millions of years of evolutionary chemistry in action, as water molecules reclaim their bonding territories from the cellulose fibers that temporarily held them at bay.
Thank you for watching. Please like and subscribe.